All right. There we are. It's not September 21st, 2022. That's okay. Wanted to acknowledge, actually in my mind it probably is, but in any case, long story, but I won't do that. I'll just want to acknowledge USTAR, the Utah Science, Technology, and Research Initiative, which is a state agency formed by former Governor John Huntsman, funded all of our laboratory equipment at EGI for CO2 research, as well as created the some of the staff lines and faculty lines fellowships in our group. So USTAR big doesn't exist anymore, but it's still the lines are still there. The Department of Energy, all of the research that I'll discuss today is funded by both DOE and USTAR, and then of course it's National Energy Technology Laboratory, which is the funding arm of the DOE, which also has a really stellar in-house research team with which we collaborate quite a lot. So, and of course EGI and the group, several former members of the group pictured here, several current members of the group pictured here as well. This was, if you notice the time, I love to show this photograph because it's at 3:35 and the proposal was due at 4 o'clock, and we were working on it right then. So kind of the mode that we've been in for 20 years now, and it's a good one. But motivations for today's session, but also all of EGI's carbon research, as well as a tremendous amount of collaborative effort, a lot of work that they've led on independently, but also collaborated with us. The Utah Geological Survey, just a lot of work that we've done in northern Utah as a team, collaborative team. It's just been terrific. The goals of that is to really manage the impact. We all assume that carbon dioxide is causing global warming. There's some good arguments to make against that, and that's great for a discussion over a carbonated beverage, but we will store our own CO2, but we all acknowledge that it's the most likely culprit, and we try to manage that impact. And then the technological impact, I'd argue that a lot of what we've done with CO2 storage research, as well as its predecessor oil and gas research, has spawned a lot of innovation, hundreds and hundreds of patents, and just really it's furthered overall research, especially in the deep subsurface. But we're moving through what we all call the energy transition from fossil fuel energy to renewables and sustainable long-term energy, such as geothermal energy, which will eventually, hopefully in our lifetime, eclipse fossil fuels. That's not likely to be the case, so we need to manage CO2 in the short term. So we want to adapt to that changing environment during the energy transition, and then minimize the risks and the associated damages that might come about, because they are possible. Seismologists, I'm talking to you, who can do seismicity. So EGI's approach, national goals, translating those to local, regional goals, how to best capitalize on what the country needs, but also what Utah needs specifically. But then also the entire, to use the word oil patch, because again, CO2 storage started in the oil patch. It will continue there as well. What are those local needs? What are the national needs? So I'm going backward. Trying not to. Okay. Someone play some music for me? Okay. All right. Yes, the Jeopardy thing. So I'm going to talk a little bit about today, although I'd really like to talk a lot today about direct air capture and the synergy of CO2, trying to capitalize on overall energy chains, if you will, and also CO2 storage with geothermal energy. Fervo Energy, who is you'll have heard from and will hear from during this discussion. They just were awarded a combined direct air capture geothermal energy project. It's the way things are moving right now. And the symbiosis already exists between the oil and gas industry and CCS, but other energy sectors are now coming in line with that. And it's a natural transition. So I'd argue, and this is again another discussion for another glass of carbonated beverage, coupling commercial scale storage to DAC is absolutely essential. So both in the short term and the long term. So in terms of a SWOT diagram, love to show this in proposals and in project reports, but also occasionally in a presentation. The strengths, the weaknesses, the threats, and what I don't have listed on here, but in terms of technological threats, I'd contend that the primary one is induced seismicity if it's not done properly. But so far, it hasn't been done properly. The oil and gas industry hasn't had any major, okay, CO2 beverage time. Let's 45Q is if the 45Q doesn't expand, I guess I should back up. Strengths and opportunities. I want to point out 45Q. It's a tax incentive framework designed to motivate industry to adopt CCS. Massive tax credits. $45, I think it's $50 per ton now for CO2 EOR, $85 per ton for non-EOR CO2 storage, and $180 for direct air capture source CO2. So it's significant. Think about a typical small power plant, coal-fired power plant, typical is 1 million tons per year. Do the math. It's a significant economic advantage to drive CO2 storage. That's in place right now, put in place by actually over 10 years ago, but then reinforced and strengthened tremendously by the Trump administration in 2018. And we do have a, much like with all government programs, it's an existential threat to 45Q and all things related. So that is an opportunity that becomes a threat if it's not extended. But I do have a couple slides about 45Q in a little bit. Move on to it. And EGI is working with 2 DAC projects, both the Fervo project and Arizona State also has a DAC hub project in place. It's under negotiation right now. Ultimately, the Fed is investing $2.5 billion in direct air capture of CO2 and associated projects and storage. What we're here to talk about this afternoon. So this is on the Arizona State campus. We've got a number of these down there, and you may see them pop up on this campus as well. So, okay. 2002, rewind all the way back to 2002 when I took sabbatical from New Mexico Tech, located here. And I spent my sabbatical year at EGI. Came up and I was in, I think what is now Al Walker's office. For a year. And Dave Curtis, Ray Levy, all of the geological folks on staff, but then G&G department, Craig Forster, UGS, Tom Chidsey, Craig Morgan, big group of people. We put together the Southwest, a proposal for the Southwest Partnership, Regional Partnership on Carbon Sequestration. We initially called it the Southwest Partnership for Carbon Sequestration, but actually literally got a phone call from the Sierra Club about that. So we changed it to the Southwest Regional Partnership on Carbon Sequestration. I'm not joking. This is, you can't make this stuff up. There was 7 regional partnerships funded starting at that time in late 2002, early 2003. This project is still ongoing today, right now. It will end next July. We'll have 21 plus years. And its sister project now is, or its successor is called CUSP. I'll talk about that in a moment. The SWP, as I'll call it, we focus on what we call the string of pearls, existing CO2 pipelines throughout the region, existing CO2 sources throughout the region, connecting those sources to sinks with those pipelines and new pipelines, exploiting existing in-place storage opportunities, which are actually tremendous. Billions of tons of capacity in this region. Hundreds of millions in Utah alone of tons of CO2 capacity. Exploiting that capacity for oil recovery is probably, I mean, it's unavoidable. Using it potentially as a working fluid in geothermal systems, EGI systems, not unavoidable, but would be darned interesting to carry out. Eileen Zabrowski, yes, she's going to start blushing now, is working on some analyses of that nexus. So it's really great stuff. But this map shows some of the major pipelines. More pipelines on since we made this map. Rich Hester made this map using UGS data 2012 and then expanded the map. It's grown even more, but all of the yellow dots are the sources, stationary sources of CO2, including coal-fired power plants, cement plants, ethanol plants, yada, 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 yada. It's a lot of CO2 sources in the region, a lot of storage opportunities as well. So we cataloged from 2002 until 2005, we cataloged all the sources and sinks. We continue to update that since then. And then from 2005 until 2012, we carried out 4 projects. Anna Field in southern Utah, Paradox Basin, the Fruitland Coal in the San Juan Basin, an ECBM project with ConocoPhillips, and then Sackrock Field, Permian Basin, enhanced oil recovery. And in those projects alone, we stored over 1 million tons of CO2. The ECBM project being the smallest at what we projected to be a 75,000 ton capacity, but turned out to be 18 because of cold swelling. We forecasted the cold swelling, but clearly underestimated it. So, all right, the goal of phase 3 now, which let me deliberately back up this time. The phase 3 project right here on this pipeline, sourced originally from an ethanol and a fertilizer plant. So all anthropogenic CO2, natural CO2. Those previous CO2 tests I mentioned were all natural CO2 sourced from the Kelmo Dome. This one was all anthropogenic CO2, so net CO2 storage for enhanced oil recovery. All of the CO2 injected in that site will stay in that site ultimately. So a lot of CO2 storage. Now, you start to factor in the combustion of the oil that's produced as a result of it, then the calculus changes up a bit. But regardless, that oil will be produced, combusted, and produce CO2 no matter what. So it's net positive. It's what it turns out to be. So we're here now in the Farnsworth field in northern Anadarko, or the western Anadarko Basin, and have injected well over 1 million tons there. So the project, EGI's projects have, in collaboration with UGS and a lot of other people, I want to emphasize that, injected well over 2.5 million tons of CO2 so far. And seems like we've monitored every drop, but it's after 20 years, you kind of say that, oh my gosh, I've seen too much CO2. So we focused a great deal. Again, back up deliberately. Great amount of our efforts has been on monitoring design and risk assessment and uncertainty quantification. Ting Shao, who will talk to us later today, is dedicated half of her professional life on UQ. And it's, I think, second to induced seismicity, which Dr. McCormack will talk about. Probably already have talked about in the last, yeah, but you will. It's the uncertainty is the other massive risk. I say risk because if we don't get a handle on it, if we don't have a handle on it, then things kind of can go wrong. So, but we've got a good handle on it, we feel. All right, the Farnsworth Field, northern Anadarko Basin. Normally pressured, not overpressured. Primary recovery, 11 million barrels. Secondary recovery, 26 million barrels. It's a prolific field. CO2 has made a big difference, though. Hopefully I show the oil production as a function of CO2 injection in the moment. But this is the close-up of the field with individual, you can see red, pink, green, yellow. These are individual 5-spot patterns that were drilled over time. I believe I have a graphic showing when they were drilled in just a moment. The western half is all CO2 EOR. The eastern half is still this conventional non-CO2 recovery, water recovery. And that eastern half is waiting on capital for infrastructure, also available CO2, but the price of oil is high, but probably not high enough to make that happen. That's another quote unquote risk associated with CO2 storage is CO2 sources, which are tied to economic markets. So here's another nicer photograph. Here's the fertilizer plant. Here's the ethanol plant. It feeds the Farnsworth unit as well as the Booker field. And there's multiple smaller pipelines spurs off of this now that are feeding other fields at this time, or preparing to. And this is a photograph of the fertilizer plant, this of the ethanol plant. So pretty innocuous looking industrial plants, but put out a great deal of CO2. Each of these about 100,000 tons per year. Only 10% of a typical coal-fired power plant, but there's a lot more of these than there are coal-fired power plants. So tackling that source is a big deal. And in the early stages of this project, the operator captured, which was Chaparral Energy, was bought out by Purdue, was a company that is related to Bill Townsend. He's one of the owners of that. Bill Townsend actually lives here in the valley, Salt Lake City. Long time pipeline buyer and owner. So anyway, Chaparral, then Purdue, and they initially produced around 110,000, 105,000 tons each, captured that and transported. When oil prices dropped multiple times over the past decade, it's been reduced down to just about 100,000 tons now per year. There's that graphic with the timing of those patterns, which stopped dead in their tracks in 2016 because of oil prices. The ultimate plan was to expand these with. This graphic was put together by Rich Esser. He was the director manager of our CO2 monitoring program for all of our projects. It was super. Aaron Meyer is here today. We'll talk a bit about just a moment ago, talk quite a bit about the air monitoring, CO2, as well as methane monitoring work that's still ongoing today. What's also a really great, and I think I have a slide on it, is the tracer work that Rich and Pete Rose worked together on for several years. Pete Rose here at EGI, and is a tremendously interesting outcome. 5 minutes? Okay. I better hurry up. Okay, so USDW monitoring, it's monitoring of groundwater. Ting Shao, who talked later in a little while, headed up this part of the project of the Ogallala Aquifer, the largest produced aquifer in the United States. She assessed heavy metals release, potential for heavy metals release, among other things, but an exhaustive analysis on out of reservoir, above reservoir pressures. Here, so I'm going to close out with this graphic, maybe skip up a few, but I want you to notice that this is the tracer source. These are aqueous tracers, naphthalene sulfate, aqueous tracers. And again, Rich and Pete designed this program. They traveled through the field, put naphthalene sulfonate in this source well, and you can see the diameter of the circle is proportional to the amount of detection. but the time of breakthrough is indicated here. Injection here, 8 days later, breakthrough. 189 days, breakthrough. 11 days, breakthrough. 42 days, breakthrough. 8 days, breakthrough. So some really extremely unpredicted outcomes of that tracer analysis. And we were able to take the seismic data, interpret the seismologists were able to take the seismic data, interpret what the geologists insisted on calling fault-like features. We would not commit to calling them faults, but definitively high permeability pathways. Lots of carbonated beverages consumed over that one. So vapor phase tracers, not so useful at all. We did try an expanded vapor phase tracer program, but for the supercritical CO2, but yeah, just wasn't going to happen. Again, Aaron will talk about the atmospheric flux data. This is as of October 2021, late. Again, we've injected net over 2.5 million tons. The net storage, though, is over 1 million tons. So pretty interesting, really successful project. I would love to talk about the seismic results. And actually, we have some really fantastic induced seismicity results from the Anna field. But I think I'm right on time. So the rest of the group is going to lay on some great, I'm giving you the 50,000 foot view. They're going to go down to the 500 foot view for you. And I'll take any questions for a couple minutes. It's CUSP, the successor. A lot of projects going there. Oh, and Nate's Iron Mountain project.
Yeah, all the folks you mentioned are going to talk about this thing.
Yeah, it's and they are just as excited as I am about it. Yes. Just very, very high permeability pathways. I insist that they're faults, but the geologists insist that they're not. It's but they are interpreted in the geology. Yeah. Yeah. Right next to each other, there will be breakthrough of, even though they're screened in the same interval, it's breakthrough at 42 days, right next to one that's a breakthrough at 8 days. So it's. It's
Thank you, Brian. Okay, we're going to start walking through a bit of Brian's legacy as we talk to his students, or his students talk to us today. Dr. King Chow came to the University of Utah in about 2012. She had a bachelor's and a master's at that point in time with Harvard Institute of Technology in China. And while she was here, she earned her master's and her PhD while working at EGI. Proudly, she was a co-PI with Brian McPherson on carbon safe, and she'll talk a bit more about that right now. So, if you would, Dr. King Chow.
Thank you, Al. So, hello, my name is Xing Xiao. I'm a research assistant professor at EGI. I'm really glad to give you an overview on the quantitative risk assessment in our CCUS project. So first of all, I want to acknowledge our funding provided by US DOE and NETL through a series of CCUS projects. And as Brian mentioned, we have a 20+ year SWP project, and I will use a lot of examples from the results of this project. And now we have our current, the CUS. It's a regional initiative project. This is the sister project of SWP. And we also have a bunch of carbon save projects. And we study the feasibility of future CCUS hubs in the Western US. And here I also list many of our collaborators from academia, state geologic surveys and policymakers, national laboratories, research institutes, and industry. So here, Brian also showed this picture, and I will show it again, why we do carbon capture, utilization, and storage. So to avoid CO2 emission to the atmosphere, we try to capture it and inject it into subsurface. The formations include oil and gas reservoirs, coal seams, and deep saline reservoirs. So now with the net zero emission in 2050, determined by the US government, and also the high encouragement of tax credit for 45Q. So the CCUS project will be very heavily invested and evaluated in the next few decades. So with the CCUS project, we have two major concerns or questions. The first one is whether CO2 can be successfully stored in the subsurface. Another one is whether CO2 can be safely stored for a long term, for example, 1,000 years. As well, when we apply the permits of Class 6 wells, we need, it's a request of redoing risk assessment. So here is our steps of evaluate risks associated with CCS. And first of all, we make a plan, and then we try to identify the risk factors. We do qualitative and quantitative risk assessment, and we have a plan of the risk response and also the monitoring plan in the future. So today I will focus on the quantitative risk assessment because it's connect our risk identification and also the planning of responses. And it provides some very reliable outcomes for our plans. So here, first step, we need to identify risk. And we collect all experts and we do brainstorming. So this picture was provided from our lead of our risk and identification workshop. And I asked him for a photo of our workshop, but he said, "Oh, do you ask for this one?" So unfortunately, we didn't take a photo when we really do this discussion. And then after we have a list of the potential risks, we do some qualitative risk assessment by evaluate their severity and likelihood. So by multiple different numbers, we have a final rank of each risk factors. And so for a CCUS project, we identify several factors of top risks. That includes when CO2 is injected into a reservoir, we're curious about where the CO2 goes and what's the capacity of the storage reservoir to hold that much CO2. And we also concerned about CO2 leakage through wells and cap docks. Also, the induced seismicity is another concern. And we are afraid that when CO2 leaks to underground source of drinking water, that might be a contamination of the drinking water sources. As well, once it goes further up to the surface, it's a huge problem. So these are some technical risks we identify. We also have some interesting results from this qualitative risk assessment of some non-technical risks. For example, the oil price and also the US government policy. So when we do quantitative risk assessment, we first of all, we define some uncertainty parameters, the components, and we heavily rely on numerical simulations. And then using those simulation results, we forecast the risks and their uncertainty. So because we rely heavily on numerical simulations, so we do our best to make the simulation models reliable. So we validate the models with all the characterization, monitoring, and laboratory data to do our best to make our forecast reasonable. And here are some methods we use. So initially, we use a conventional method called Monte Carlo simulation, but then we want to save some computational time, and we reduce order models, uncertainty quantification, and more recent machine learning techniques. So after CO2 is injected into the deep reservoirs, it starts to flow, and it is trapped by the cap rock, and also it can be trapped in the pore space by residual trapping, and also dissolve into the brine by solubility trapping. For a longer term, it can form new minerals. It's mineral trapping. So during this process, we have several questions. Can this reservoir hold that much CO2, and what's the storage capacity? And with the well, we want to confirm the long-term injectivity. And we also want to know where the plume goes and in what phase. That's the storage mechanisms. After a long term, with the new mineral formation, we want to know whether this mineral trapped the pore space and pore throat, and that might be a concern of storage capacity loss. So we did a bunch of studies to answer those questions. So we forecast the CO2 plume and their phase by using different parameters. For example, the relative permeability. And overall, we can forecast the overall shape of the CO2 plume. But in some places, we still see some different results. So that requires more monitoring and characterization tools to answer which one is right. And we also forecast how much CO2 can be stored in a reservoir, and as well, the oil production with CO2 EOR. Then we want to design some optimization options that make sure we can store the maximum of CO2 as well as we produce more oil. So this is an example of our design of maximum injection with water alternating gas. We also did some analysis of the storage capacity loss with mineralization. So for this one, our result is for a few hundred years, the mineralization won't impact the capacity too much, only like a few percent of loss. So one concern, the biggest concern is the leakage risk. So after CO2 is injected into the reservoir, it might leak, both through the wells and cap rock. And once it arrives to the shallow groundwater aquifers, we start to concern about the water quality. So here is the pathways of leakage, the wells, the cap rocks, fractures, and faults. So here is a picture of a well. CO2 might leak directly through the well casing, and also possibly from the wellbore cement. Also possible through the gap between the wellbore cement and the formation rock. And most of studies think that it's the highest possible that CO2 leads to the wellbore cement. So we studied this aspect most. Because once CO2 interact with cement, they react, and CO2 might cause the cement lose its structure and integrity. We did a numerical simulation study at the interface between cement and caprock, and we assume that there is a small gap between these two formations. And the simulation results show that there is a little cross decrease at the interface because the calcite precipitation. So that might further prevent CO2 intrusion into the caprock, into the cement for a few hundred years. So our CCS project might be successful. So our takeaways are, we find that legacy wells are considered with more risks. And if we only consider some fractures in the wellbore cement, and the leakage will be minimal. And if we consider the worst case scenario with open hole of the well, the leakage can be lead to 0.4 to 1% of the total injection CO2. But which is still acceptable within 1,000 years. Okay. So we also studied the leakage through caprocks. So long-term safety relies on caprock, and leakage mechanism include diffusion, capillary pressure breakthrough, and fractures. And from our studies, the caprocks may maintain their long-term integrity. So we also did some numerical simulations at the interface between the reservoir and caprock, and we also found some cross decrease at that interface. So in this case study, our caprock is also safe. The key concern of the CCUS project is the leakage into underground sources of drinking water, because it's harmful to our water safety. Because there's no leakage shown in the existing CCS projects, we assume some CO2 leaks into the underground sources of drinking water, and we use simulations to forecast the impact area, and we also forecast the water chemistry parameters, that what's the range of those parameters after CO2 intrusion. We also make some estimate of the likelihood of such impact. So we found that monitoring data is very important to detect any leakage and guide risk assessment. And backward, the risk assessment also very important for our plan of monitoring strategy. And here is another big concern, the induced seismicity. So once CO2 is injected into the reservoir, the pore pressure changes. And once the stress state break through the failure criteria, the fault might slip, and that can be a seismic source. And Kevin will give a more detailed presentation on that. And here's an example of our SWP project. We have a very fancy monitoring tool in the well. And during a few years, we detected hundreds of events of microseismicity. And those the magnitude of those events are ranging from -1 to 0.5. So if we don't have that tool, maybe we will never detect such small microseismicity. So it's really important that we collect a lot of data. But now there are not many data in our CCUS project, so we use a lot of data from water injection or in oil industry. Yeah, so that's this is my summary. With the goal of net zero greenhouse gas emission by 2050 and also the 45Q tax credit, CCUS will be heavily invested in the next few decades. And risk assessment is very important for any CCUS project. The risk and uncertainty quantifications of CO2 behavior in the reservoir, the leakage, impact to USCWs and surface and induced seismicity are all studied and quantitatively with advanced techniques in our group. And that's my presentation. Thank you.
Any questions? Thanks.
So you talk about 1,000-year horizon. They're trying to figure out and also tomorrow. But at a certain point, doesn't the carbon dioxide minimize?
The reaction starts once CO2 is injected into the reservoir, but it's not significant until a few hundred years later. Yeah. Yeah. So yeah. Mm-hmm. 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 Yeah, so our project is a CO2 EOR project. So the pressure is well controlled. I think that's why. Yeah, for both the pressure and the CO2 plume reach to the well. If the CO2 plume never goes to the well, there won't be any. Yeah, so in our case study, we use the real well locations. Yeah.
I guess EPA has certain steps or certain standards you need to proceed through to getting approval of an injection well.
Yes.
Are these standards adequate, or are they paying any attention to your risk assessment, or are they what decided and don't even meet your?
The quantitative risk assessment is requested when we apply for the well permit. So we need to show EPA that the risk is low enough to get the permit.
You have to know the specific steps that you need to step. When you qualify, and you qualify, you want to be adequate for being a licensing of a well injection.
Right, quite well.
So my question was,
Yeah, it's very heavy over.
Okay, thank you, Doctor. Okay. Okay, well, our next speaker is Aaron Meyer, and Aaron is coming to us from Los Alamos, my first talk to you, wasn't it? Or San Diego? Okay, all right, so he was out in New Mexico someplace. Comes to us with a Bachelor of Science in Math, and also earned a Master's in Civil Engineering here at the University of Utah. He's going to talk today about the novel approaches on monitoring, verification, and NDA on greenhouse gases. So,
All right, is this working? Sounds like it.
yeah, we're good.
Great. Hello, everyone. As Ellen said, I'm Aaron Meyer. I've started my career here at the University of Utah with Dr. McPherson. I'm one of the many that he's mentored into a researcher. And I know we have a lot of great minds who spend a lot of their time with their heads underground, thinking about subsurface stuff. So for a brief period, we can come up into the sunlight and the fresh air. And I'd like to talk about specifically atmospheric monitoring of CO2 and methane in order to basically make sure that these gases are staying where we anticipate them to be throughout their lifetime. So monitoring these big assets, either in the context of oil and gas extraction or CO2 injection, is really difficult because, as you see here, this is a screen grab from Google Earth. If you've ever flown over the Permian Basin, it's a huge pincushion, and the potential leaks of methane or CO2, these harmful greenhouse gases, they're generally localized to specific well pads, processing facilities, faults, etc. But these localized sources, emission sources to the atmosphere, are then spread across this vast region. And so we have invisible gases potentially leaking. How do we see them? How do we find where they are and mitigate that that chance of those harmful emissions making it into the atmosphere and kind of doing more harm than good as they warm the earth? And so this requires some level of monitoring, verification of keeping those gases where we think they should be, underground or in pipelines, et cetera. And so we require monitoring, and even more with provisions in the Inflation Reduction Act, methane taxes on emissions, et cetera. How do we monitor this? Well, in kind of going through the gamut of different techniques, what I've come to the realization, and I think the community as well, is that it really requires a dynamic, multi-scale system that leverages advantages of the different techniques that we're using to be able to detect fugitive emissions of both CO2 in an injection framework or methane in all oil and gas extraction activities. And these are often proxies. If there's something leaking if there's methane leaking from underground, there perhaps is also CO2 from an injection reservoir. So Dr. McPherson said that he gave the 50,000 foot view, and we're going to narrow down. I'm narrowed down, and then I'm coming back out to satellites, so we'll get more than the 50,000 foot view. And all of this really started with Dr. McPherson noticing this vent here on the upper right, which is the hood of a Panda Express in the University of Utah Union. And he said, why don't you go stick your head in that for a couple of years, come out smelling like orange chicken. I don't recommend that. But what it is a really nice case study. It's a big source. We know where it is. We can measure it. We can directly measure how much emissions are coming out. And so the goal of this, my master's thesis, was to set up different types of in situ monitors around this known vent and develop techniques to be able to tell where a potential source was and how big it was. So what I did was set up a few towers on the roof of the Union and then looked at the data. So statistically, what I was able to find is that these hyperlocal, what I'm calling hyperlocal point sources, can be pretty well characterized by these in situ ground-based or tower-based monitors, especially at near scales. And so if you're near a source like a well pad or a processing facility, you can do a decent job of characterizing what your emissions may or may not be. In the context of an oil and gas extraction field or injection field, these have some benefits in that you can deploy a distributed network, which provides kind of a smoke alarm approach for when you're seeing elevated levels of methane. Well, near the well that we installed that sensor, we can anticipate that there's emissions from there and go about trying to characterize how big they are. There's a few different techniques that we can use in machine learning and statistics that do a good job of this, but really it's a localized solution, and instrumenting the entire Permian Basin, for example, is a challenge because it would require tens of thousands of sensors all working harmoniously. And so this is kind of the narrowest view that gives us a good idea of the size of emissions and where they're coming from. But then I moved on to Los Alamos National Lab, where I got to bring myself out of the Panda Express and look at a different vent, which was the vent of a coal mine vent shaft, venting all of the coal off-gassing from the underground coal mine, and install a similar system of in situ sensors, so gathering a little bit of air and analyzing how much methane or CO2 or other gases there are, and put it on, in this case, my Subaru, and drive around a field where we knew there were a lot of emission sources. In this case, this was the San Juan Basin in northern New Mexico. And what we were able to see here is that by actually looking at different gases, different hydrocarbons specifically, we could start to do something I called fingerprinting or source aggregate or disaggregation from one another. And so certain hydrocarbons emit or are characterized by different levels of higher hydrocarbons. So ethane, in this case, we were measuring ethane and methane simultaneously, and then driving through these emission plumes. So the top graph there is me driving my car through a plume. It has that nice Gaussian plume-like shape that you would expect. And then plotting the ratio of ethane to methane allowed us to fingerprint or provide a signature for what kind of source that was coming from. So we have in the bottom right, you can see that big vent that's venting out the coal gas, which is generally drier, meaning there's lower levels of higher hydrocarbons like ethane. So the ethane to methane ratio is lower, flatter. And then we're also sampling gas that's wetter with higher hydrocarbon ratios. And so what this allows us to do is do some source disaggregation where in the context of, again, something like the Permian, where sometimes you have operators stacked on top of each other, there's a level of forensics that you can do using this type of signature technique, and being able to tell, well, we have a source of methane, but where exactly is it coming from? This provides us a little bit more information for characterizing that. But again, it's still an in situ laborious task to drive around to know where to look, basically. And so that kind of leads me to the work that I'm most interested in doing now, which is something called total column measurement. And so this technique leverages spectroscopy. Basically, we're gathering sunlight. We put a measurement system on the ground, gather sunlight as the sun tracks across the sky. And as that sunlight comes through the atmosphere, the different gases that are present in the atmosphere absorb sunlight at different wavelengths, and we can do some fancy physics and math to be able to back out an integrated total column measurement. So how much methane or CO2 is there in the column between the ground and the top of the atmosphere on the line on the path of the sun. And this is helpful because it's more of a regional scale measurement. You're not hamstrung by the fact that you're only measuring the gas that's near your potential sources, but instead is a broader scale view of potentially a basin. And so what we can imagine, and what I'm working on now, is trying to build a network of these, getting the costs down on the actual spectrometers themselves so that we could deploy perhaps 10 or more in a basin like the Uinta Basin near here. That gives us kind of a box model. It pulls up the curtains on the basin and allows us to see kind of hot spots of where potential emissions may be coming from. That allows us then to kind of triage sources. Where are the most important sources that operators need to go and look and do their traditional LDAR type work, and leverage then those techniques that are more well suited for sources close by, hyperlocal sources. And part of this is using pretty sophisticated modeling that was actually developed here at the U by the professor in the atmospheric science department called back trajectory modeling or stilt inversions. And so basically what we do is we make a measurement and then we set a receptor saying this is where we made our measurement. If we have a model of the wind field, the atmospheric wind field, we can run time backwards and see where that particle came from. And so in this case, this is work by someone done here at the U in the context of looking at data in Saudi Arabia. But what you can see is if we release these particles backward in time, they give us this influence footprint. So we're measuring the total column. Where do we anticipate that that measurement is sensitive to? And this is a much broader region, which helps us in the context of a big oil and gas basin. And so I actually have deployed this summer a couple of these instruments here in the Salt Lake Valley with specifically in the context of methane. You can see a few anticipated methane sources here. There's a bunch of oil and gas refineries in North Salt Lake, wastewater treatment plants and landfills. And so what we were able to do is, see if this works. This really provides a nice kind of 3D view of what's happening in a total column measurement. So the white lines here is as the sun is tracking across the sky at each hour. And then that line with the dots on it is the hour that I ran this stilt inversion. And so in this case, in this hour, we can see that most of the influence is actually coming right from that refinery row. What this allows us to do is monitor on the basin scale and provide us with these hotspots that we can then kind of narrow down and look at more closely using those techniques that are more well suited for local point sources, as this does a good job of giving us an idea of where sources are, but perhaps is not quite as adept at telling us specifically this well pad is leaking X amount of gas, but really provides us, again, kind of a forensic tool to narrow those things down. And so to bring us all the way out to the 50,000 foot view, I haven't talked much about satellites, but I think of this monitoring problem as a really an integrated approach where we get really coarse data from satellites that are orbiting, monitoring methane and CO2, but one, they're only making overpasses perhaps every couple of weeks, and you can see the grid. They're pretty coarse resolution, so they find basins that are emitting a lot of these gases. Then we can zoom in, look at techniques like this ground-based remote sensing or total column measurement to even further kind of pare down where we anticipate leaks are coming from, and then move into the more sophisticated methods for using both mobile systems and those hydrocarbon fingerprints, as well as perhaps the ground-based in situ networks that are being set up to have an integrated view of emissions on the basin scale all the way down to where they might specifically be coming from. It's this valve or it's that processing plant, which is really useful when trying to monitor such a large basin for sources that are really localized. And so with that, I will finish my time and happy to take any questions. Must have done a great job of explaining it.
Plus you didn't get the 5-minute look. Okay, I'll go ahead.
Mhm. I haven't. I actually, so I work in the atmospheric science department as well, and we had a seminar with Dr. Alex Turner at University of Washington, who exactly what you said, doing really cool work on some legacy data. Really, the satellites that we have up now are pretty good, but it's really interesting work that he's doing, being able to kind of look back at some of this data that is longer term and picking out some of these methane and CO2 trends using tools that were not necessarily designed for that, but have the information available. So I haven't done anything with it, but I'm as excited as you are because I just learned about it too.
On the integration, like, about the 30,
So I haven't made any observations in the Uinta Basin. We do have the professor I work with in the atmospheric science department, Dr. John Lynn, he has one of the longest standing in situ networks running in the Uinta Basin, and some really great work, a paper that he published in Nature about the Uinta Basin being one of the leakiest in terms of emissions versus production. And that's really one of my main goals is it's easier to deploy these. I haven't yet. It's on the list. I would really like to get these instruments out into the Uinta Basin because of the stage we're at with the actual instrumentation. It's a lot easier to do it when you can plug it into the wall on the roof of a building in a city and iron out all the issues before you try and put it in a nice dusty, snowy field. So stay tuned. Come back next year and I'll have a better graphic for you.
Thank you, Aaron.
Sure.
Okay, so we're gonna go on a 10-minute break, but before we do, Brenda, would you like to print? If you look at the pamphlet, the conference program, it's got the bios and photos of everybody in here, except for Carlos, for some reason. I didn't take care of Carlos, so. Anyway, Dr. Carlos Vega he's been at EGI now for about 5 years. He's going to talk today about the partnering of the oil and gas industry to accelerate carbon capture and utilization. And he's the appropriate speaker for that because not only has he gotten his master's in petroleum engineering and his PhD here at the University of Utah, but prior to that, he worked for Schlumberger and Pemex for 11, 12 years out in industry. So he's got a lot of that industry experience, and plus he's done his research as one of the many students of Dr. Brian. So with that, Dr. Carlos, thank you.
Thank you very much. Thanks, Alan. Well, thanks for attending the presentation. So my name is Carlos Vega. As Alan introduced, kind of introduced myself. I've been working at EGI for the last 2 years. First with under Dr. McLennan, now under Dr. McPherson. So thanks for that support. So my topic is going to be, I'm going to be giving a bit more details on why we are here, why do we care. Dr. Bill Kitch was asking all the time in these courses. Why do we care about about integrating science, academia into engineering, into the real world out there? Well, I'm going to start with this photo that I took from a website. So basically, this is like a typical atmospheric inversion in Salt Lake City at any time during winter. So there is a lot of pollution problems due to greenhouse gas. So we shouldn't get used to this. And Mexico myself, I know very well how difficult it is to break. You know, like from my hometown, there is a big refinery, big power plant, 4% sulfur fuel oil. It's just 24/7 run all the time. So it's bad, and we shouldn't get used to that. This shouldn't be the standard. So basically, motivation, more into details, the carbon cycle. So carbon cycle has existed through Earth history. So in the long term, there's like a long-term sources, long-term sinks in the terms of mineralization, volcanic eruption. But what we care the most is like the fast sink, the fast sinks is basically vegetation, forest, how all these plants use the photosynthesis to convert sugars, to convert carbon dioxide using the sun's energy into sugar to produce energy. Sources is the metabolism that we do. Like right now, as we breathe, we are metabolizing our energy to produce CO2 energy and water. But what about the anthropogenic source? So all these have been in balance, has been cycles of down for the CO2. But the point right here, and the biggest concern is the high anthropogenic source of CO2 based on the energy that we require to perform our activity. Electricity, power, transportation, all this is coming very quickly, starting from the Industrial Revolution. So these charts are different records of how the carbon dioxide has been oscillating up and down, which has mostly a trend. But lately, up to the Industrial Revolution, the CO2 emissions start like skyrocketing very high. So these history records of CO2 are basically human-made, anthropogenic source. And this is a chart of the CO2 emissions post 1850, which basically says that we have been putting a lot of CO2 combined with our activities. To the point that the biggest concern right now is the global warming. As we all know, these charts, based on the current trend, the current baseline, there is some estimations that the global temperature can increase up to 4.1, 4.8 degrees Celsius. And this will be really chaotic. It will be catastrophic to our current lifestyles, because of the rain cycles, droughts, floods. It will be really, really chaotic. So based on this UN Paris Accord, there are some initiatives from governments and industries to limit this increase on the global warming to less than 2 degrees. So that's very clear. And this is all hand by hand with the energy transition. The problem is, no problem. We need to understand and we need to learn. The energy demand right now up to 2018, that is this chart, more than 75% of the energy of the sources is coming from fossil sources. Coal, natural gas, and oil is still providing us with more than 75% of the energy that we require right now. So it's not going to be that easy to switch over to renewable energies, although that's something that we need to have in mind. So we need to increase the utilization of hydro, nuclear, others, biomass, wind, at the same time that we learn from our mistakes and learn how to use fossil fuels in a smart way. So this is what we are integrating, not only the technology far ahead for carbon capture, but also at the same time that we need to understand that oil and gas, we still need to use that, particularly in economies like developed countries. There is going to be even longer way before we can switch or start thinking about coming into this net zero, which is the ideal. So there is a long way to learn. There's a long way to understand that we need to do something with the CO2 that we are utilizing. I'm going to use this chart that I found when I was for a project that I was working in Mexico. I love this chart. Why? Because this discretized the different contributors to the CO2 or to the equivalent CO2. So here we have transport, energy, manufacturing and construction, other fugitives, industrial, residual, agriculture. So each of these has mostly CO2, but also at the same time we have methane and we have nitrogen NOxes that we have, plus additional gases. The right hand side of the chart, we have is split between the sources, that how much of this CO2 equivalent is going to atmosphere, and how much is taken naturally, almost because of photosynthesis, and also because of mineralization underground. And this is the source, or how we can understand the net zero, right? Because net zero doesn't mean don't use fossil fuels anymore. That's not the goal. The goal is to match whatever we have in the source to have the equivalent on the 6, they're just to make a match. That's total objective of the globe of the goal of the net zero goals that we should be understanding. And this is where the business model for the CCUS could be. Why? Because instead of having just natural sinks, we can increase or we can put additional reserves by implementing technologies such as carbon capture. And many companies, cement industry, they are targeting to utilize carbon capture technologies to capture more than 40% of their emissions. So additional to the strategies that they're implementing to reduce heating up, to convert the carbonates into clinker, more than the reaction itself of making elaborating the cement, there is a CO2 associated to the combustion. So many industries are looking into carbon capture to meet their goals, meet the targets towards environmental goals of this carbon capture. And this is where it can be monetized. That's right there, the aspect that we could propose as carbon capture, as oil and gas industries, to create this synergy to produce that subsurface volumetric volume available for store. So again, what is it about? Carbon capture sequestration is by utilizing several 4 different strategies, enhance all the recovery, depleted oil and gas, cold methane, and deep saline aquifers. Utilize these subsurface storage sites to permanently capture and store the CO2 that otherwise is related to atmosphere. Now, talking about oil and gas industry and the carbon capture, particularly EGI and our carbon research group. So oil and gas has been basically described as upstream, midstream, and downstream, right? Upstream meaning how do we extract fluids from underground, taking them to the surface. Midstream, how all these oil and gas or hydrocarbons are transported from the production sites into the refineries, storage pipelines, and the downstream part is refining, refining up to the point of commercialization. I like to think of the CCUS industry as a reverse process, right? First, we need to capture it, we need to store it, then we need to transport it, we need to do some processing, condition the CO2 up to the point that we are injecting and permanently stored, as my colleagues already described on this part. And oil and gas industry has tons of experience, tons of man hours of experience performing these activities. From the point of view for capture is associated with DAX, utilization is associated with the EOR, transportation, storage. There is a lot of core analysis, petrophysics, geophysics into the modeling. Operations, there is all the drilling operations, all the injection operations is based on the technology that oil and gas industry has developed over the years, as well as monitoring either as 4D seismic, DAS technologies, different strategies that we have been adapting from successful reservoir characterization into carbon capture. I'm going to talk about generally over the different projects. Yeah, over different projects that we have been working at EGI, and how we are integrating, or how we are taking all that information to databases, mostly legacy databases, into integrating this. So I'm not gonna take different details. So carbon safe phase 2 project readiness. This is led by Dr. Ting Zhao. So this is in the winter basin. The exercises that we completed here was to compile or grab legacy information in the form of petrophysical logs, and combine the information that was available. So we had hundreds of wells, but out of the hundreds of wells, only 1 or 2 had actual useful information that was perforating into the potential reservoir. So there is a lot of uncertainty right there. because looks like we could have a lot of information, but it's not the case. So there's a lot of statistical analysis, machine learning, uncertainty quantification that we could produce a valuable or a pseudo valuable data set. And then all that information was compiled, put into a three-dimensional model that Dr. Moody right here was keen to perform injection simulations to kind of foresee where is the CO2, the plume, where is it direct, and also to forecast or to perform a feasibility study that this location is suitable for a commercial or long-term carbon capture storage facility. Talking about a bit of the future steps of the project, there's a lot of planning and going regarding the well construction. So we have cement, we have casing, we have logs, drilling fluids, coring, we have rigs. So all these operational aspects for the oil and gas people is the most obvious thing. For the academics, is not. So there's a huge disconnect right there that we need to integrate our efforts to come up into a meaningful and sustainable projects. Another project, Iron Mountain as well, led by Dr. Moody here, same exercise. So we combine a lot of information that we have, evaluate, QC the petrophysical logs. These logs were from 1980 something, I believe. Yeah. So there's a different understanding, a different approach. Why? Because back then they were looking for easy oil, you know, like a super saturated, high permeability, high porosity, and the goals, even of the logging was a bit different. Then there's a huge gap on the technology that if we take different petrophysical information right now and we want to compare, there's going to be some significant statistical variations that we need to match again and to validate different ends. So a lot of petrophysical information right here to integrate in order to overcome all these questions that Dr. Shao was telling us, you know, to minimize the risk. Most likely, there is a good potential in these sites to be likewise drilling, planning for here. So there's a bit of communications lately with the different service companies on how do we approach the best drilling scenario, where to drill, where to core, how long the course it will take to have all these projects into them. Another project that is taking longer than expected. We were approached by Mexico's government on this particular state, Tamaulipas state. They wanted to take the lead into carbon capture in Mexico. There is no regulations. There is no regulation. It's different, you know. All the underground belongs to all the underground fluids and storage spaces belong to the state, belong to the country. So it's a bit more complicated because we need to go into these new strategies to put fluids down there. So there's a lot of uncertainties, like who belongs the risk, who belongs the investments, to whom belongs the different scenarios. But anyways, the plan is to perform all these different planning as if it was a conventional oil and gas. The novelty of this is when it's like we are going to target to do the analysis in a shallow water that unfortunately for Pemex was a dry well. It was they drilled a couple of wells in there. They couldn't find anything. So that's very good news for us because we learned that there is a very vast, very beautiful sandstone to act as a reservoir down there. And it's very close to the shore. There are 3 wells, exploration wells. There is very good seismic information, even 3D, that we should be able to improve. I'm going to skip this quickly just to give us a little bit of a grasp of the different laboratories that we are utilizing to simulate or to model all these different. So basically, this is a core flow testing that we are using or readapting from a dissertation to Ziri's work. I don't know if she's going to speak about it. And this is coming from Dr. Mike Lennon's efforts as well. So this is just a summary of the different publications related to carbon capture on how we are implementing or trying to collaborate with the oil and gas industry to come up with these approaches. So thank you very much. That's my presentation. Open for questions. Yes, sir.
A lot of good information about. Clarifying regulations, you know, it's really strictly analysis on story. I haven't heard a lot about what the perspective is. It's not going to be on the
Cost effectiveness of the program.
even analysis.
Yeah,
So, carbon capture.
I don't have it.
Everything. The cost range is very variable because there aren't large scale plants built yet, that it ranges anywhere from $600 to $10,000.
But I'm guessing because it's not being widespread. It's not being implemented widespread, but even with the 45%, right?
Dr. Kevin McCormick. He's no stranger to EGI. He was originally here and left back in 2009 to go to Stanford to get his training in geophysics. So he's back now as a postdoc. And so Kevin's going to talk to us now about seismicity. Yep.
Awesome, thank you. Oh, you first. Hello, good afternoon. So my name is Kevin McCormack, and I'm going to talk today about induced seismicity in carbon sequestration. I'm a research scientist here at the Energy and Geoscience Institute, and let's get underway. So, oops, I don't know where to go. So just as an outline of the talk, I'm going to start with a brief introduction, talk about sort of the mechanics of induced seismicity, and then we'll talk about probabilistic hazard prediction at a site in New Mexico, in the San Juan Basin in New Mexico. And then we'll talk about fault curvature, how the curvature of a fault might impact seismic potential, or at least seismic hazard potential. And that'll again be at the site in the San Juan Basin in New Mexico. So moving on to our brief introduction. So as we know, if we inject a fluid into the subsurface, it pressurizes the formation you inject into. That pressurization has a poroelastic effect around the region of pressurization. And that if it impacts a fault that's present just in situ in the earth, that can host an earthquake, and it can host a large earthquake. I mean, it's possible. And so we really want to avoid that. Just as a community, we want to avoid having a large scale earthquake from carbon sequestration, from hydraulic fracturing, from EGS. We just don't want these big events. And so the majority of this talk is going to be focused on just trying to avoid hazard in these carbon sequestration projects. And so just as an anecdote, what we're really trying to avoid is losing the social license to operate. So in I think it was 2011, a magnitude 2.3, that's not a terribly large earthquake. A magnitude 2.3 caused the United Kingdom to put a 3-year moratorium on hydraulic fracturing, just because they lost the social license to operate. So just hounding the point a bit, but we don't want these events. So what is the mechanism by which these events occur? Well, if you increase that pore pressure and you cause these faults to pressurize, the fluid in the fault supports some of the normal stress because fluid can support normal stress. However, it doesn't support any of the shear stress resolved along the fault because fluids can't support shear stress. It's why S waves don't travel through fluids. And so what happens is we decrease the effective normal stress on the fault, and that causes the Coulomb failure function to increase. And so what that means in terms of a Moore circle is we have an initial stress state here, and that change in pressurization causes the effective stress to change and bring the stress state closer to the failure envelope, which is how these earthquakes can occur. Now, there are many other mechanisms by which these earthquakes can happen. It's not just the pressurization of a fault. You can also have poroelastic effects, which, as I mentioned at the start, when you have that injection zone, that pressurized zone, the region around it gets perturbed by the fluid holding some of the stress. And so that can cause changes in the Moore circle and the stress state. And then you can also have thermal mechanical effects, which is essentially where if you have a fluid that's at room temperature at the surface and you inject it deep into the subsurface, it's much cooler at the surface and the subsurface is much warmer. And so you have a kind of a thermal shocking effect, and that can cause changes in the stress state as well. And then finally, you can have Coulomb stress transfer, which is where if a fault slips at one location, the region around the fault, the stresses in the region around the fault get perturbed such that you can change the stress state. And if the conditions are right, the orientations are right, you can actually bring faults to fail because a different fault failed. And so all of this is really well understood. This has been understood since 1890, I think, is when Otto Moore first develops his Moore circles. And what we're in the sort of the technique we're trying to do is we're trying to understand this Coulomb failure function, this CFF, which is the distance from the pole, which is the point in the Moore circle that represents the fault, to the failure envelope. And this is a function of the shear stress, the effective normal stress, and the coefficient of friction, which if you just sort of look at it and think about geometry, makes perfect sense. And we want to look in this talk, what we're going to do is we're going to look at how how this well understood system, it's been well understood for more than 100 years, how this system can be understood. We can have a better granularity of the understanding of the system. And what we'll look at specifically in this talk is probabilistic Moore circles, where we actually take input parameter distributions and vary them in a Monte Carlo sense and create a probability, a distribution of the Coulomb failure function. And then in the second part of the talk, we'll look at how the curvature of a fault. So instead of having a single pole that represents a fault plane, we won't use a plane, we'll use a distribution of the fault planes, the orientations of the fault planes, and that will lead us to a more spatial understanding of hazard along the fault. So without further ado, let's get into probabilistic hazard prediction. So this stems from the San Juan Basin Carbon Safe Project. You've heard about it a little bit. It's led by William Apamo at New Mexico Tech. And it's a commercial feasibility test of carbon sequestration. It's in the San Juan Basin in northwestern New Mexico. It's intending to store a lot of carbon dioxide. It's trying to be a big storage hub. And they're even applying for more funding as we speak for additional resources to do even more with the project. And so it's currently applying as well for a Class 6 permit, as we were talking about before. And this is to have the license to actually inject the CO2 into the subsurface. And so the first thing that I like to do in these sorts of studies is look at what is the seismicity that's taken place in the past. So this red outline indicates the basin boundary. The hogback monocline in green indicates the structural formation that is of interest to us in this study, as you'll see in a second. In this green region in light green is the area of interest for the project. Now, these green triangles represent the seismic stations, the stations that record the data. And these little dots are the seismic events. They're color-coded by their magnitudes. And the thing I'll point out two things really quickly. One is that the majority of the seismicity concentrates along the periphery of the basin, and that's mostly due to the structural complexity of the periphery of the basin. In the center of the basin, it's sort of competent flatline strata where you just don't have as many faults present, so you don't host as many earthquakes. So the other thing I'll point out is that in the region of interest, especially along the hogback monocline, we have very few events that were recorded by our network. So the first thing, or I suppose the second thing you do is you want to look at the state of stress. You want to say, okay, so what are the stresses acting in this basin? And so we use the extended Eaton's method, which is not the greatest method for understanding stresses, but it gives us a start. And what we see in this plot here of depth versus stress is that the two horizontal principal stresses are very close together. It's a radial normal faulting environment, and that'll be important in a moment. The other thing we need to do as we sort of get our input data is we need to look at what faults are we aware of? What faults are present in the basin that might host these large events that we want to avoid? And so when we look at these faults, we found 5 faulting scenarios. These are 5 possible scenarios that may be of interest. However, there's this one, the hogback flexural faulting area in the top there, that is of more interest because of what I'll show later. And I wanted to describe what this is. This is a series of faults that have been folded as the monocline took place, and you had the competent strata that folded and slipped past each other in flexural faults, which created discontinuities in the surface or in the subsurface, and which represent the boundaries between the strata. And these and so you have a series of subparallel faults representing these hogback flexural faulting area. Now, when we do our probabilistic Moore circles, we take distributions of the input data. We do a Monte Carlo approach, 20,000 realizations for each scenario, and we get a distribution of the Coulomb failure function for each of the 5 scenarios we are aware of. And so there's this one, the hogback flexural faulting scenario, that's higher than the rest. It has a higher hazard than the rest. It's closer to failure than the rest. And so we need to inspect that a little more carefully. And so, as I was saying, these are these strata that have been folded and slipped past each other. And we are also aware of about 20 million barrels of wastewater that's been injected into the same formation that's been proposed for the carbon sequestration. And this is sort of a pressurization test that's taken place. And because of this, or at least while this is taking place, we've also not seen much seismicity. That figure I showed at the start really didn't show much seismicity. And so we think what's going on with this area is that instead of having a big, large fault that can host a large earthquake, you have all these subparallel faults from the flexing of the basin. And as a result of that, you have microseismic events and the seismic slippage gets distributed along all those subparallel faults. So the last thing we can do with an analysis like this is look at the sensitivity of each of the input parameters. So on the x-axis, you see the Coulomb failure function. On the y-axis, you see the different input parameters that we put into the model. And so the dip is always a strong sensitivity, and the strike in the least principal or in the SH max orientation are always low sensitivity, and that's because of what we know about the stress state and the orientation of the fault. The dip is a very uncertain parameter, so we used a very large distribution for the dip, and so we couldn't. And so as a result of that, we have a very large sensitivity on the dip. It's just 1-to-1. And then for the SH max orientation in the strike, we know it's radial normal faulting, and so because of that, the strike of the fault is not very relevant to its stability in the stress field. And so because of that, these two parameters really aren't very relevant in the study. And to also note is that this principal stresses are intermediate in most of these figures. So in summary of this section of the talk, the input stresses and orientation are required to run this analysis. The injection appears to be safe for most of the region of interest, but the flexural faults did have a high Coulomb failure function. And then by looking at the saltwater disposal in the geologic framework, we can realize that the hazard really may not be very significant. So thank you. And let's move on to the fault curvature section of the. Oh no. So the fault curvature section of the talk, we can observe that in many previous studies they use a planar approximation of a fault. So they just say the fault is planar, but we're aware that in geological situations there's roughness defaults, there's rugosity defaults, and there's curvature defaults. All of these are not planar features. And so we took a realization of those hogback flexural faults that I was just talking about, this point cloud that curves with depth because we know that the basin is curving like that. And so we discretized these faults into these close packed hexagonal spheres where any data that came into a sphere was analyzed together. And so what it does is it discretizes the analysis of the fault based on where you are on the fault. And so we have a discretized version of the fault. And we did Bayes' law. So this is a Bayes diagram. We started with the data for where the orientation of the fault is. We go up through a regression to get a dip and a strike, a distribution of the dip and the strike, which we feed into a geomechanical model. And we put the input parameters that we used as distributions for the first part of the talk into the geomechanical model and created a Coulomb failure function, which is a distribution of the Coulomb failure functions for each of the discretized points. And we also did this with Krieg models. So we did this for all of the points in used together for the Krieg model, and we did it for each of the individual spheres for the discretized model. So what this looks like is you have these spheres where these are the discretized models with different levels of discretization. And you can see that we've actually highlighted a region in the fault that has a higher hazard than the rest of the regions. And so if we look at the Krieg model, we have the Coulomb failure function, which is a function of location along the fault. And so that's the hazard changes depending on where you are on the fault. And so in summary of this part of the talk, when we have information about the curvature of the fault, this could be a useful technique. It's not just the orientation of the fault that changes the curvature of the fault, but also the state of stress can change from one portion from one depth to another. And so that's a factor that comes into this as well. And then this is not applicable for all situations. You may actually be better off using a planar fault for many situations. And so in summary of the overall talk, we have the probabilistic hazard prediction section, which indicated what the hazard, or at least a distribution of what the hazard is on different locations, different fault scenarios. And then also we had the fault curvature section, which gave us a spatial understanding on the hazard of the fault. I'm sorry I went over. Yeah. There is a difference. There's definitely a difference. And what I think it has to do with, so you realize that like the planar is just like one realization. And then the discretized version, you have a ton of realizations. And the difference is like, especially in the discretized, the spherical discretization, I think there are edge effects to that. And so I think the overall hazard becomes lessened. But generally they're about the same, as if I remember right. Yeah. Uh-huh. Well, so we had data from the amount of pressurization we expected from the carbon sequestration, but then there was also we had to use an input parameter for what we expected the pore pressure to be in situ, and I honestly can't remember. I think we must have taken that into account, but I'm not sure. Oh. Yeah, so we did. In that case we did, yeah.
We gave him all the data.
All right, thank you.
Well, Kevin, explain two very complex.
That's my phone.
Thank you so much. Now we're going to squish two speakers into a 20-minute talk here. Yeah, this is going to be a tag team of Dr. Nate Moody and Rob Simmons. And we're going to shift a little bit to, it's been very, very geeky, if you would, during most of this discussion. We're going to talk a little bit about how all this teaching is impact politics. That would be a good transition to so I'm going to hand it off to Dr. Moody, who's got his PhD here at the U. Rob Simmons, who's got his law degree here also at the U. Have at it.
Thanks, Al. All right, we'll start off today with we're gonna bring it back to kind of more high level view, less minutia in the details of all the studies, but we will be bringing kind of bits and pieces of all these different studies together, because really what we've all heard today is all of the science, and you've heard the word modeling over and over and over again today, and then some talk of policy. So really we kind of wanted to bring this together, is how does all of this talk of our modeling, our science, all of these things we come up with, how does that then translate into policy action, or we hope policy action? Because in the CCUS, not much has happened yet. So just to start this off, kind of, we have what I'm calling concept execution. So we come up with a project, whether that's Ting Xiao's proposal that we put together, which is some of this data, or it's one of the projects that we've been approved and we're trying to execute. The first thing you do is you come up with a conceptual model. You got to have a model of what you're doing, or what are we going to do, where are we going to do it, and that there is going to inform your next step, which is your data gathering. Where are you going to gather the data? What types? Where do we have data gaps? And then you're going to start moving down the chain of understanding that data, characterizing it, helping you build a picture of the site you may be looking at, such as that's the Uinta Basin over there from one of our models. And then we're going to get more and more detail. We're bringing all of this data into our models. We're going to make more complex models. We build models on top of models. And then you start doing analysis to understand all these different scenarios that may happen, so that we can answer questions of risk. We can answer questions of storage capacity. And then once we've done all of our geeky stuff and our science, and we bring it together, we've got to present it to somebody. We've got to present it to people. We've got to inform them of what we've come up with. Like, what are our findings? Does this matter? Is this a good storage site? Did you invest your money well with us? All of these great questions. And so I'll kind of run through the steps in general of kind of what we do there. And so this has taken some data out of Dr. Xiao's
proposal along with some other data from the Iron Mountain project that I've been working on. And so here we have, this is kind of a conceptual model. We have your area of interest. We have where we're going to be grabbing our CO2, areas where we want to inject it. So it's kind of, this is where we want to be. So now let's find the data that's there. Well, we've got many types of data that we can grab. We can grab rocks from outcrop. We can grab core out of the ground, which is like better than gold. Amazing. Give me all of it. We can make thin sections out of stuff. And that's generally just raw data. Like there's no modeling that goes into drilling the core plug, pulling that, that's just the raw data. But then we can get stuff like seismic. For the raw data, you can't view the raw data. So this has to be processed through some sort of model to even get a raw line, basically, what we would see, that first pass on it. Same with well logs. Now, I'm not a big well log fan, but or a big well log guy. I don't know the most about it, but and some of those tools are just measuring the response of, you're measuring the response of your reservoir as it goes down, whether it's neutrons or density or whatever. And you would have to generally run that through some sort of model to get a usable curve out of it and some usable data that you can then move on to our next step with, which is now we need to kind of synthesize this data. We need to derive the properties that are of interest from us from all of this raw data that we've gathered, whether that's well logs and using these old correlation models that were come up with, in the 50s and 60s, or maybe even earlier for these. And use our well logs to come up with porosity and permeability, because we're going to need that for our modeling steps further on for our detailed numerical modeling. We're going to need to measure properties of our rock cores, whether it's capillary pressures or relative permeabilities or densities or any of those type of things. And all of those, your measurements are generally where you've got pressure, inlet, outlet pressure, amount of fluid intruded, like those are your parameters. And so you have to run those through some sort of model to come up with, which is a relative permeability curve. That's not what comes out of the machine when you run the test. You then have to run it through some sort of model to get that data out that then you're going to use in your next steps in modeling. So as you can see, like basically almost every step we go, modeling is critical step in the process. And I mean, you've heard that over and over again all day, modeling, modeling, modeling. And so this is just kind of the next step and this can apply to almost any industry, right? We just know subsurface, so this is how I'm presenting it. But we start synthesizing all this together. So what do we need to do here with the group that's here? Well, we need to understand the geologic characterization. We need to know, is there faults there? Is there leakage pathways? Abandoned wells? Is the subsurface even good to store? Oh, it's great in the basin and range, and then we see a cross section of seismic in the basin and range, and you go, nope, that's no good there. So you've got to synthesize all your data together into another model, and then you can use that model to start planning things like, where's my uncertainty, where's my data gaps. We can start looking at plans to address questions, and so that's where we come to the next bit. Is now that we've synthesized all this data, we then make it coarser. We upscale it into simulation models that have very large cells, and we've taken all this fine data that all of you people have put together for us, and we just make it really coarse so that we can run it through a computer, and it doesn't take 6 weeks to run the model. It takes 2 days. I got one that just finished after 6 days. I don't think I'm going to do that one again. But as you can see, it's just kind of, we need to then do this so that we can get some answers as to what may happen in the future. So if we want to inject, say, 50 million tons, I'm going to use this case study from Dr. Shallow's proposal. Do we want to use 50 million tons into a single formation, end up with a plume that's, it almost stays within the boundaries of our property that we wanted, a little bit outside, and we're just taking advantage of one storage reservoir? Or do we want to take advantage of our second storage reservoir that's deeper? Now we have stack storage, we have a smaller plume size. And so that's what this numerical simulation modeling is. We can start looking at all these different scenarios. We can put leaky wells in there, we can put faults in there, all that type of stuff. And start getting at all of these risk quantification questions, these uncertainty questions, and just questions of storage security and things that regulators are going to want to know. Can you store it? Does it flow towards possible outcrops or towards possible faults and stuff like that? How am I doing on time? You're great. Okay. 'Cause I think I got one more. So that's kind of, we're synthesizing this, we're doing all our numerical simulations. And now we have to present this data. And can I get the second one to run? Yeah, okay. And so generally what we do is when we present this, you're presenting as reports, posters, you're at conferences, stuff like that. And so a lot of times it's images like this. We've seen lots of images like this today where we have a site, or we have images like this. This is Tim from Ting Xiao's carbon safe. And so this is basically we're looking at a cutaway of the storage reservoir. These are what I would really love to show people. This is what comes out of my simulations, is these time series data. We got gigabytes of data. We've got these great, and I've got multiple properties that we can look at. But this is very difficult to show people unless I'm in a forum like this. I can't write a manuscript and have this go with my manuscript, or I give a poster presentation, or you give a report, right, to the DOE. It doesn't contain this that shows them how the CO2 moves. So there's challenges to how we present the data. And that's just a couple more examples. Like this is from our successful proposal that Ting wrote. I mean, so we have, bottom hole pressures, and I think this is injection rates and stuff, just basically data showing that this site held 50 million tons and answered the questions that the DOE wanted answered. And so there's just many ways that we can present the data. And of course, we've seen that all today with everybody's presentations with all these great charts and graphs and everything. And so that's how we get to the data. And now Rob will tell us how we can then move this into the policy. So with that.
Great, thanks. Yeah, thanks, Dr. Moody. So a question for everybody. How do you make good decisions? Yeah, so this is the big question in science, in policy. But in policy, it's really important you make good decisions, that you have a very accurate view of the world and the systems which exist within the world. And then you make good decisions which lead to good policies, good laws that lead to really good outcomes for people and citizens. So any thoughts on what makes it for a good decision? Well, I'm sure there's a lot. Anyways, but the way you get to good decisions is experience. And experience, though, sometimes can be very costly. And so the question is, how do you get experience? And the answer is by making bad decisions. And that's true in policy. So in policy, there's a big history of, hey, we made bad decisions. We had really bad outcomes. We learned very slowly from it. And so then we, when real catastrophes happen, or we see like these slow moving train that's coming at us like climate change, we say, okay, we finally need to do something about this. And that's not a great way to do policy. And so the next question is, where do we want to make our mistakes in policy and in science? The answer is in the lab or in models. So Dr. Moody was showing a lot of the modeling work he's done. You want to make your mistakes on the computer and in the lab and in places where they're not going to hurt people. You don't want to make all your mistakes in the real world. You're certainly going to make some of your mistakes in the real world, but you don't want to make all of them there. So just really big picture on the goals with reducing carbon emissions and greenhouse gas emissions. So the United Nations Intergovernmental Panel on Climate Change and International Energy Agency, and you can also include the United States Department of Energy. They also support carbon capture and sequestration as a crucial low carbon technology needed to achieve societal climate goals. And this is a really important point too. Carbon capture and sequestration isn't just important for its application to power generation, either natural gas or coal. But there's a lot of industrial processes that are extremely important to the quality of life which all of us enjoy or will want, our fellow sort of global citizens to enjoy. That includes the creation of cement, steel, fertilizers, and all of these create a lot of CO2. And so even if you were able to switch over from fossil fuels, and the only way to really realistically do that is through a widespread adoption of probably nuclear power with our current understanding of sort of what's possible and how much it costs. But because that's unlikely, And because, as I think someone said earlier, that the clock is ticking, we have to look at every option, every tool we have. And so one of those tools is carbon capture and sequestration. This I won't discuss too much, probably don't have enough time, but this is one of our projects. It's led by Dr. Moody. It's the Iron Mountain Project. It's down in southern Utah by a town called Cedar City. There's an iron, it's in Iron County, so you can imagine there's an iron mine there. And there's a company, Utah Iron, who wants to develop an iron refining plant. And they also want to include in their design and in their execution the ability to capture the CO2 and then sequester it. So we're looking at that. And this is just sort of a pretty high level workflow. And the point of this, and it all culminates in this permit you get either from the United States Environmental Protection Agency or, as I'll talk about later, the state of Utah. But it's a very complex regulation, maybe one of the most expensive and complex that has ever been created. And that's not necessarily criticism. That's aside from the argument whether it should be, it just is very complex and expensive. And so all this whole process, you're talking about time, you're talking about a lot of people and complexity and overcoming a lot of challenges and working in certain areas which are not yet fully sort of tested. And you're talking about a big expense. And so then the question is, well, how are you going to get people to do that, especially industry, because that's the end goal. So we're part of what's called the Carbon Utilization and Storage Partnership, which is all these states in the West. The goal of this partnership is to get industry to adopt carbon capture and sequestration, to make it easier, to de-risk it is one of the things we've been talking about, but to make it less expensive, to make it less risky, to help address liability, address a lot of the issues that keep industry from investing more aggressively in this area. So in policy, there's carrots and sticks. There's either incentives or punishment. And so you always want to start with the incentives. And so the federal government put in place what is probably one of the more powerful or significant tax incentives ever created, which is the 45Q tax credits. We talked about some of those today. You get $60 for every metric ton of carbon dioxide that you inject as part of an enhanced oil recovery project. Or you can even go up from there and you get $85 a metric ton if you do CO2 for every ton of CO2 you inject as part of a non-EOR project, injecting into another geologic formation, such as, let's say, a deep saline aquifer or sandstone or whatever's a suitable target. And then you get $85 a ton. And then if you really want to get as much tax incentive as possible, if you do direct air capture, it's up to $185 a ton for every metric ton of carbon dioxide captured and stored permanently. So the carrots are fun, but as I knew, because of, I'm getting older, and so I had some experience with policy, when you have the carrots, behind the carrots come the sticks. And so this spring, the U.S. Environmental Protection Agency proposed a new rule, and this is quite a bit of a summary, but it's a very complex rule. But this new rule will require pretty much all fossil fuel power plants to install CCS technology by 2035. So there's the stick that will follow these incentives. I won't talk too much about this, but the reason why we're thinking about carbon capture and sequestration in Utah, at least from a policy standpoint, is because it's a great place to do carbon capture and sequestration. There's great geology. This map, the darker the color, the better the estimated amount of CO2 you can store safely and permanently in the subsurface. And this is hundreds of millions of tons of storage capacity. And so out of this, and I won't have too much time to talk about this, but basically the same things that our team is looking at on the science, the engineering, the modeling, is the same things that matter to policymakers. They want a good, accurate picture of what the system looks like. So if it's in the subsurface, what's that system look like, so that they can start addressing sort of what policies are needed to address, to solve problems. Modeling and simulations, like I said before, you want to avoid making all your mistakes in the real world. You want to make as many as possible in a virtual world. So monitoring, verification, accounting, this is absolutely crucial. The only way sort of policy or law works is if you have a way to account for it, to measure things, to make sure that you know what amount of CO2 went into the ground, how much stayed there, where it's traveling. And then you have to deal with risks. Risks to drinking water, sources of drinking water, underground ones, as well as we talked about seismic risks, and there's several other risks, but you want to make sure that you address risk. You'll never make any policy if you try to avoid any risk. So you're just trying to make sure that the risks are manageable and reasonable. Oh, yeah. So this is just a little bit of an overview of how complex the policy landscape can be and the regulatory landscape. And so I won't go into this too much, but in Utah, you can have federal lands, state lands, tribal lands, private lands, of course, and all of those you have to apply a variety of different federal statutes, and there's a whole lot of them. So more importantly, when you're trying to make good policy, it helps to have, these assets like the Energy and Geoscience Institute that can inform good policy, can give us, the policymakers, a good idea of what things are known, what things are not known, what the risks are, etc. So where the scientists work in labs, where good policy starts is at the Black Bear Diner, where Representative Steve Handy said he would meet me. So I'd worked with Steve Handy for quite a while on different projects and different things in energy and air quality. And he was known as one of the best legislators on those issues, as well as somebody who was willing to stick his neck out and look at sort of forward-thinking policy. And so I had breakfast with him, and that started some important discussions about him sponsoring some state legislation. And so Utah, in the 2022 legislative session, based on a lot of work, John Baza, Director John Baza with the Division of Oil, Gas, and Mining was a big help, the Utah Geologic Survey, our team. But we put together what I think is the best legislation in the country for addressing a lot of the issues we talked about, addressing liability, ownership issues, critical legal issues. And a lot of that's based on what the team, the different researchers and scientists and the people we assembled were telling me and helped inform the policy that was passed, or the statute that was passed. All right. And so this is bringing it all together. You've heard quite a bit about this project out in the Una Basin, which is where most of Utah's oil and gas is produced. We have a great project, which really the science is informing the policy, but also the policy is informing the science. So this big block of blue is state trust land. This is important because all state trust lands, they're managed to benefit the school kids here in Utah. So all the revenues that are generated by development on state trust lands will go to the school systems and the school kids. And so our scientists said, hey, this might be a great place to inject. There's good geology beneath it, and it might be the ideal place to have a project. And I agree from the policy standpoint because, one, you have a big landowner, and then you also have a very sort of sympathetic landowner. So as you sort of work with the different stakeholders on why this project's important, it definitely helps with that. Then you have a big source of CO2, Bonanza Power Plant, which is a coal plant. You have a great existing, well, it's gone through an environmental impact statement, and it's been approved for a utility corridor. So you got something that could connect the CO2 pipeline from the source, the actual sink. And then what's interesting here is this is some models that Dr. Moody put together, but you can actually make some choices based on policy consideration. So, for example, if you want all of, and Dr. Moody assured me that he didn't do this to sort of meet my policy goals. It's straight science. But these plumes, as they're modeled, are staying on the state trust lands. Yeah, no, I went through with a big eraser and like kind of erased anything that kind of went over. But
I'm gonna have to pull the original model.
What's great about this is you can make good decisions. Because, for example, you can look at stacked storage. Different. You can look at different geologic sort of formations that are at different depths. If you wanted to stay with one landowner, or if you've got a lot of good landowners, then you can spread it out. So just in conclusion, you know, the modeling and science definitely make the better policy, but also the policy can, you know, inform the science and the engineering so that they know what to focus on. And that's it. I'm in the.
Okay, our last panel today is going to be on carbon sequestration. And Eric Edelman's going to lead this panel and be the moderator. Eric's he got his master's in petroleum engineering from here. And I think he did it when you were in Saudi Arabia, but he did it remotely with the program that we have here. And then came here and finished up PhD in civil engineering. So Eric's been back here. He's got a lot of industry experience, having worked for Schlumberger, Saudi Arabia. So Eric, take over.
All right. You turn that one off. Is it going to echo if I stand over here? Okay. All right. So we have an outline or a great panel to present, but real quick, I wanted to canvass the audience for some feedback on topics of interest. I did hear some policy interest. We went a little deep with the science, and I wanted to hear if there were specific topics within the group. You know, you've been able to sit here for about 8 hours quiet, so now you get about 2 seconds to talk. So any feedback?
Was deep with the science of pun?
Ah, that was good. I'm not that smart. I didn't come up with that. Any specific topics, policy, capture methodology, transportation. Nate. Okay. Okay. All right. We do have a question for that one.
I saw on an earlier slide that the current global emissions of 40 billion tons annually. I think the U.S. has 5 billion ton contributions there, right? Given that factor, I'd like to figure out if anybody thinks that we can build enough plants to make a dent.
Yeah, we're gonna get there towards the end, but that is a good one. Anybody else? Now's the time. Speak or deal with my questions. Steve's got a plan in place. We're going to talk about that in a minute. Steve doesn't realize that, but we'll hear it.
This bill has opened the door to minority opinions. Something we should have done at the beginning of the government and the public should have done it on, but looking at the complete analysis for carbon dioxide emissions. For example, is it for certain that all of the carbon capture and sequestration for sure reduces more carbon dioxide than it actually creates in the process?
Okay.
I can comment on that when we get there.
We're gonna get. I want you to formulate your thoughts around some of these ideas. If not, then we'll hit them as we go. Any other questions or items we'd like to focus on for the discussion? That's an exciting one. I'm really excited about that. There are ways to mitigate that, and Brian's got it figured out.
Capture question, but capture sources over here in Utah.
This is good. We will talk about Utah. All right. Anybody else? Requests? All right. We're going to take off. So we are pleased to have a wonderful panel, a diverse panel, and we're going to give them each about 2 minutes to present themselves. Eugene, I'm going to get your name right. Zamansky. I had it. I work really closely with Eugene so we can laugh about it. But Eugene, would you mind giving a brief overview of your background and entertain the audience for a minute?
Okay, thank you. I brought my planning group. So my name is Eugene Zamansky. I'm a senior geologist at the Utah Geological Survey. My experience and expertise is in characterizing the geological conditions and subsurface. I've done that for about 12 plus years before working for Chevron, our global prevention group, and now here on the applying the same skill set to Utah, which has
about as diverse of subset conditions across the state as I've seen around the world in my previous job. So I work with Eric and with Nate and others on that Iron Mountain carbon capture and storage project that was mentioned. I can speak a little bit specifically about that if people have questions. And also the geological survey, I'm proud to say that we just landed our first major DOE grant to do statewide carbon sequestration assessment and to work with both private sector partners and build information databases that are also public friendly. Because the more this is talked about, the more people want to engage with the EGS about it, and putting that information in context to them is important for us.
Great. All right, next up we have Steve Handy. Steve, do you mind giving us an intro?
Good afternoon, everyone. I'm really happy to be here. This is very exciting. I have a lot of nice friends here in the audience that I've worked with before and lots of things, but I'm here because someone thought it was a good idea that I should run for the Utah legislature. And I got elected. And when I came in, it was about 12 years in the House of Representatives, and when I came in as senior legislator, my background has been in communications. Remember when we used to have newspapers? I was a marketing director and probably didn't do a very good job for two of Utah daily newspapers, but no, the internet disrupted it, you know. But anyway, so that's been my skill set, communications, and so a senior legislator said, Steve, he said, what do you know about energy policy? Would you like to know more? I said, I don't know anything about it. He said, I think you're perfectly suited for it. Let me train you, and I'll mold you the way that I want it. So anyway, it kicked off, and I've had just amazing things that happened and opportunities that come to me in opportunities for policy, and good policy and good legislation in the state of Utah, including the bill that Rob referenced that we did together with John Baza here also and others in this room, Dr. Pearson was helpful, and we did in 2022. So just a little bit. So now I'm not in office now, but I have lots of things going on in the energy policy area, and I'm asked to speak a lot too. So that's a lot. I was in Colorado 2 weeks ago. So go ahead.
Wonderful. Eileen Vance.
In Conoco Philly. So I was selected to be here because Conoco for the last 2 years we've been looking to go into the CCUS. First, the cleaning side, mostly the Gulf Coast, also looking at other states, and now trying to make them a reality. My background is mostly as an exploration geology, international, offshore, but there are a lot of traits somebody else. A lot of skills that you can translate to CCS and something that I'm also working on at the company.
Wonderful. Brian McPherson.
Brian McPherson, again, I'll also say thank you so much for attending today. I'm really grateful to be here. And I like to call myself a hydrogeologist. I've been a faculty member with EGI since 2006. I've done a lot of work on CCS for the years.
Perfect. Reed Page.
Hey everyone, thanks for giving me the opportunity to be here with all of you. It's been a really cool day. Learned a lot of interesting things. A lot of things that went way over my head, but it was all enjoyable so far. I am Director of Gas Marketing Operations for Summit Energy and Integrated Energy Companies, privately owned, actually employee-owned group of companies here in downtown Salt Lake City, not far from here. Originally, I'm actually from Roosevelt, Utah. So I'm intimately familiar with the Uinta Basin. Also, for the last 10 years, I've been involved in gas marketing and trade, as I mentioned before, and scheduling. So I see how natural gas moves and value moves from place to place, from supply to demand. And by kind of being involved in all of that for the last decade, it's allowed me to be able to intuit kind of very quickly how economics work for other things, not just natural gas. And so in the last couple of years, I've been involved in discussions around carbon capture and sequestration, as well as a few other things with a development partner out of the East Coast of Washington, D.C., Solar Power Partners. And so we've been paying a very close attention to all the activity surrounding CCUS and related technologies, and also geothermal, as has been mentioned, and the combination of potentially geothermal, CCUS, and hydrogen as well is a big conversation for tomorrow, I guess. But all of these things. So I'm just very, very excited to kind of bring a commercial and market an economic perspective, none of the technical. That's why I have all of you guys. And I'm really happy to be here.
All right, well, let's jump into it. Eugene. Here we go. Why is it essential in the context of, oh, okay. Carbon sequestration. Why are we here? What are we looking to do?
So, I understand, some of the comments, this very early offset about, helping set decisions about the amount of impact that we may be able to make given the relative volumes of globally, all the here in the United States. I'm not here to necessarily advocate for carbon sequestration policy, but as a scientist, I try to look at corollaries in things like the space program to think about why we should be working now instead of later. So the more we can build technologies now, learn from our mistakes, if it turns out that this really is going to be impactful, is going to be useful in the future, and we've started that groundwork already with potentially scale up after that. But why in Utah in particular? You want to speak a little about the geology of it?
I mean, yeah, let's go for it.
So Utah has a fairly limited set of point sources. When we refer to point sources, they may be cement plants, fertilizer plants, coal-fired power plants, where we can directly capture CO2 from an emissions stack and then sequester it underground. There are fewer and fewer of those point sources that are just naturally becoming less with due to economic forces, things like California also not buying power generated by fossil fuels, things like that. But Utah has a not great amount of open space, including places like the West Desert, where once new technology like direct air capture may come to a more efficient, they could be deployed and energy captured from the air directly, sequestered directly underground, almost anywhere in the state. We have reservoirs at feasible pressures and temperatures underground where CO2 could be sequestered. So it's important for Utah to pay attention to this in particular, because we need to do the groundwork in order to implement new technology and funding solutions.
Okay. We'll step forward just a touch. Let's jump to policy, Steve. How about that one? Just talking about what Eugene had brought up. You've helped pass the House Bill 244, the geologic carbon sequestration in 2022 in the Utah legislation session. Why did you feel that it was necessary to aid in that? And how could we as engineers, or questions that were presented earlier, what could be done to help bring the importance of carbon sequestration out to legislation or to the public?
Yeah, thanks a lot, Eric. When I was approached on the legislation, I knew just really enough to be dangerous about it. I didn't know enough about it, but what really got my attention was the opportunities for economic development, and the fact that what we were trying to do in the legislation was attain primacy that Wyoming and which Dakota is it, North or South? North Dakota has already primacy. And so we are a very business friendly and a states' right state. And so that was the policy direction. So that we wanted to, yes, we want to control our destiny. And then you had at the initial committee hearing, I recall, a business came in, wants to do a cement plant, or it was a fertilizer plant somewhere in southern Utah or central Utah. And they, bringing in $1 billion, and that gets people's attention. We want to inject the emissions. And we talked all about the geology, all about the science, and that helped policymakers as well. We don't, I'm a Republican, but we don't usually talk in our this is a super red state. We don't usually talk about, climate change. That's a difficult subject. But what is not a difficult subject is economic development and talking about reducing emissions. Everyone gets that. Everyone wants a more carbon, a less carbon intensive future. Everyone can understand that. If it's affordable and reliable, how do we do that? And, not on the back of taxpayers, but if industry wants to do it, and they want to get entrepreneurs take off at it and invest all kinds of millions of dollars, why wouldn't we want to do that? And so that was where we went with the policy. And it was like I say, it was difficult to explain. I'm probably saying more than you asked me, Eric, but difficult to explain the science, but we explained enough. Dr. McPherson came, we explained enough, and others came that they got it. But to talk about, all of these other benefits that I just articulated, that was the way that we got it done. And the whole issue of the primacy argument was, yes, of course, we want to do that. We want to be in control of our own destiny. And that's the way we were able to get it done. And, when you talk about 6 or 7 years to get there, it's ridiculous. It's craziness to be able to get there and get that primacy.
So, great contribution. And panel members want to chime in. I think Eugene, you have a comment to follow up on it.
I just wanted to emphasize the economic argument, especially in states like Utah. So specifically for the Iron Mountain carbon sequestration project that we're doing in Iron County, that is literally tied to domestication of the steel supply. So the iron ore is currently mined in Iron County. It's out of country. Steel is made, steel is imported. If we can actually make steel. It's stupid. But exactly. So if we could actually take the iron ore out of the ground, sequester and make steel on site, and sequester the carbon dioxide on site as well, it eliminates all that transport and all the unnecessary engagement outside of the country. Thank you.
Following up on that from an industry perspective, what are your thoughts on how CCS policies can be improved to better collaborate with industry?
Like at this point when some states are very close to having that time, they are not even clear in classes when construction guidelines. So that is it's a very strong possibility that having that line that the state having clear construction guidelines can help the labor to
Brian, kind of moving things forward with carbon sequestration, what major concerns do you have or do you think should be addressed through the sequestration process?
Well, as Sid asked about, the time required to deploy it is, and as each of the other three panelists have already outlined, the time required to go from soup to nuts, cradle to grave, whatever you want to say, it's a long period of time, and just the economic factors that promote or inhibit are also uncertain. So there's a lot of ducks that need to line up to make it happen. That's number one. Point number two is just as Dr. McCormack laid out, induced seismicity. It's the moment that a significant event is induced that will throw a lot more monkeys in the wrench. So it's absolutely critical to avoid that first significant event.
So induced seismicity. So to follow up on that, what methods for monitoring CO2 are mandated by the federal government to date?
Well, to get back to the policy, EPA Class 6 is the primary mechanism for enforcing that monitoring. It's a nominal 50-year post-injection site care period monitoring that can be reduced to 2.5 decades or even shorter. But it's effectively in industry terms, that's in perpetuity. And so who adopts that when that monitoring regime when a company is sold? And will that inhibit transfer of ownership of companies and marketplace trading because of that fiscal period associated with monitoring? Your question is what are the requirements? There's groundwater monitoring, there's pressure monitoring for, again, sediment seismicity, air quality monitoring that Aaron talked about. And the details of all of those are pretty extensive, but it's basically covering surface, near surface, and then of course in situ. And it is, as was outlined, someone mentioned it earlier, Nate, I think, was responding to one of the questions. It's Sid's question earlier on. It's actually more rigorous than most other, except for maybe class 1, which is radioactive waste storage and otherwise. It's more rigorous than most other forms of required monitoring care.
So Reed, here's a question for you, transportation. Can you describe the methods and infrastructure used to transport captured CO2 to storage sites?
Yeah. Yeah, so I guess it depends on if you're transporting superficial CO2 versus just pressurized CO2. But you can transport CO2 in coiled tubing, honestly, under the right conditions, and under other conditions you have to transport it in stainless steel in 316, and you want to avoid that because that's super expensive. But it's piped around.
So what road?
Yeah, you get to the site and have to obviously for infection.
So we've kind of talked about the storage standpoint. What kind of hurdles are there in place for the transportation to be implemented? Is it easy to get a pipeline or to transport CO2 to site?
I think intrastate, it shouldn't be significantly more difficult than, actually it might be easier than transporting and getting. Maybe it's about the same for building an intrastate methane pipeline. I'm not 100%, I'm not sure what the hurdles are if you were crossing state lines for something like this, because, well, would you then be perk-regulated because you crossed the state? It's technically not even an energy gas, and so is it then subject to perk? Is it just Department of Transportation service? Like there's a list of unknowns there, but I do not think that it's going to be a significant problem.
Okay. Those unknowns are reduced as long as rights of way are identified up front.
So continue with the risk. Eugene, are there any adverse environmental or ecological effects associated with localized storage of CO2, and how may they be mitigated?
So I think it kind of goes a little bit to what Brian said. There's still potential contamination of underground groundwater aquifers. Those types of geologic hazards, are not necessarily high risk to the public, but they certainly grab attention. Right. So this is really why there's an important step for geologic site characterization before any holes are built in the ground or any factories are built or any retrofitting is done at a plant. You need to understand what the subsurface conditions are like, and we not only collect a lot of geological data to go into models like Jake has shown, where you see the extent of the plume very continuously sitting in the reef. But the point of doing all of that is to anticipate these problems coming down the line. Deep seismicity, I think Kevin McCormick can speak a lot more about this. We're not talking about something that is going to be shaking up the whole valley, right? But enough in deep seismicity in some EOR in the oil and gas field is enough to grab people who tend to become frightened about it. Sometimes for different reasons, if it comes to leakage to the surface of those noxious gases. For Utah, also, as I mentioned, groundwater aquifer contamination. One of the things that we want to do before we think about injection is to make sure that water will never have any other use. We'll never have agricultural use. We'll never have, potable water use for people. So it would basically be water that is, saltier than the ocean that would never be used for any other potential use other than maybe as the aluminum for food.
That was pretty good. Steve, kind of progressing this, as the political figure, reaching out to communities, engaging with them, we're a bunch of scientists for the most part, and we're not as socially skilled. Much of the public is still skeptical of these of carbon sequestration or coming into their neighborhood to store inject fluids. How would you recommend within the community, within the scientific community, to reach out to these individuals to help them understand what we're doing? I mean, you talk about working with politicians to get this bill moved forward. How do we engage the community effectively?
Well, I think that you do that by, of course, it's an education process, and sometimes it can be a slow education process. And sometimes in these community outreach things, you can get pretty surprised about where the opposition comes from. It can be really, really crazy. The folks from our Office of Energy Development know that I've been also involved in the Western Interstate Hydrogen initiative on the communication side that we're doing with Utah, Colorado, New Mexico, and Wyoming. And what has been so interesting to me is that we have 3 big projects in New Mexico, and the New Mexico legislature is, not in favor of hydrogen. The Native American tribes there are pushing back because they've been, who knows why? We don't know why. But when the federal government funds the 1.25 billion project that the eight projects are asking for, there will be a massive community outreach effort to educate people one-on-one if necessary, in homes, in wherever it is, to educate them. This is a workforce opportunity. This is a sustainability opportunity. This is an opportunity for economic development. This is an opportunity to address climate change, whether you believe in that or not, but certainly to reduce emissions. And this is the new world. And as a communications professional, I'm really excited about the opportunity to talk honestly and with integrity and with good facts to people, and remove the emotion from things. And sometimes that's impossible when you're talking about policy. We all understand that. I certainly understand that. But it's going to be a really great challenge. And the same thing, what I just gave you about what I know about hydrogen, the same thing about CCS. Those opportunities will be there to communicate in an honest and an effective way, and using those kinds of things. This is safe. This is proven in the lab. This is something that will bring economic development, jobs. This is good for your community, and it will be great for the environment. Those are winning arguments that skilled people will have to certainly make.
Thank you. Eileen, question for you from the industry standpoint, with a reluctance to pay more than $85 per ton by the federal government, and given the current cost of storage and pipeline infrastructure, how does this affect the overall economic feasibility of the different carbon capture solutions? Thank you. We're gonna jump to Reed real quick. Reed, question for you. Up to this point, within the state of Utah, within the group here, where are good or the highest CO2 emitters in the state? Like, and do you know that by chance? I don't know. I can go to Brian.
The highest point source. CO2
Point source,
emitters in the
yes.
state.
Yeah, that would like potential capture
Oh, with the potential.
that we could potentially capture.
economic for capture.
No, let's just throw it all out there.
Just the general.
Yeah,
Oh, well, let's throw economics out completely, capture everything.
telling an economist that isn't a good idea, but humor me.
Well, so, I don't know, the points, most of the point sources have been reviewed. Like the big point sources have been looked at, and I think the economics are gonna be very, very difficult. It's in particular, the coal plants. Coal plants are just, the more likely scenario is going to be a replacement of those coal plants with natural gas that is, there'll be combined cycle plants that are ready for sequestration, that are ready for capture and sequestration, whether or not they have capture the moment that they are put into service, or if it's going to be, let's say, a couple of years later, because we're still waiting on, you know, X, Y, or Z, primacy, et cetera, some additional CO2 takeaway infrastructure. My focus is really going to be on new sources. It's going to be on facilities.
What kind of new
facilities
sources?
that were built with the full intention of being ready again for a bolt-on or sequestering from day one, or sorry, capturing from day one. And so the sources that I like, obviously, I like natural gas power plants, you know, but I think that SMR, hydrogen production, and we talk about hydrogen hubs and all these things. Hydrogen production for any number of things, but Steve actually mentioned a project that was they were looking at using coal, converting coal to ammonia. It was a coal to ammonia process, and they were going to capture it, and that was going to produce an ungodly amount of CO2. It would still be really cool to see that happen. But ammonia production is a really, really big one. That's a massive piece of our CO2 emissions globally. That's what, 3%? I think 3 or 4%. So that's a big piece, and that's not a shrinking market, the production of ammonia. So blue ammonia, I really like renewable biojet fuel for decarbonizing skies at some point in the future. I have a lot of issues, obviously, with the RFS, the renewable fuel standard, and a whole bunch of other things. But I think that's going to be one of the last fuels that it's going to be very, very difficult to fully, like, we're not going to be, I don't believe for a moment we're going to be electrifying skies anytime soon. So that's going to be one of the very last carbon fuels for transportation in particular that it's going to make a lot of sense for us to use bio or renewable processes, which would include, you know, hydrotreating and again, some more stuff. And then the other hard to decarbonize stuff like concrete and steel. Steel's already mentioned. Concrete would be really, really interesting. But again, the way that it sits right now in the state of Utah, all of these sources are sort of disparate and weird places that you can't just bolt on, capture on all of them and somehow aggregate their volume of emissions. It makes a lot more sense for us to see a co-location of industrials in a few key locations, could be down in Iron County, because as soon as you have a project that is injecting, that is sequestering, it creates sort of a center of mass and gravity for other industrials to show up, co-locate. We also like, obviously, like Wellington area in Carbon County. And then I'm really curious about the potential for southeastern New England County. Anything in addition to potentially just capturing the emissions from power generation sources. I'm curious about what else could happen out there. There's an issue there with remoteness. You can't manufacture a ton of things that then need to be moved out of that area in the absence of a rail connection. It's a whole other story, right? In case rail. So yeah, it's going to be, I think the future for Utah is going to be a lot of new large industrial sources as soon as we can get the 5 points of infrastructure sort of figured out in its potential respective location.
Thank you. Brian, following up on that, legacy carbon sequestration projects that have been implemented, what have we learned from either successes or failures from projects like FutureGen? What can we take from those to improve what might be implemented going forward?
FutureGen, which never really happened. So I mean, I say that because I loved your comment about ammonia fertilizer plants, iron processing plants. Those are static. They're not as subject to the economic forces that natural gas and coal might be. Drastic global reduction in CO2 emissions following unconventional fracking and natural gas production expansion. Dramatic. So much so that, you know, President Obama was like, oh, we've reduced the emissions by X percentage. And it was really the price and drop in the price of gas that brought on that reduction in emissions. And, you know, natural gas combustion emissions are right at 50% of coal-fired emissions. So it is a great transitional approach. But get back to your question about the legacy projects. It's what we identified in some of our EGI's legacy projects is that the economic drivers of the CO2 sources was so significant. That's, you know, Ting discussed the qualitative risk assessment and then even the subsequent quantitative risk assessment protocol that all projects through Class 6 applications are mandated to implement. Main risk is economic. It's not the technical risks. Among the technical risks, the biggest one is Dr. McCormack's induced seismicity. It's really induced seismicity, man. It's induced seismicity is the most major significant technical risk, but it's dwarfed by the economic risk, and that's still holds true. Without the incentives, as you just said a moment ago, without the 45Q economic incentives, that is inhibited in a big way, and those economic risks become even larger.
So I think it was no, forgot your name. No, last row. You made a comment. Yes, Eric. Yes, Eric. You made a comment earlier, and you're talking about the financial incentives. This was during your presentation. You're talking about the financial responsibility that we have as emitters for the economics associated with the output in the atmosphere. I flush a toilet. I water the lawn. We are liable to pay for infrastructure. We turn our car. We buy gas. We turn our engine. We release it into the atmosphere. We don't have liability. We don't pay for that emission. And that's something that I felt was a very poignant and very direct and applicable item here, especially if we are to capture and sequester CO2. CO2 at the moment, capturing, it doesn't make money. It is an expenditure. But from a responsibility or accountability standpoint within the environment, we need to take that into account. Eugene, geology. You know a little bit about that? All right. What areas within the state exhibit good attributes for CO2 storage, and what might be some of the limitations you see within those regions, like orientation, fractures, I don't know, or faulting, like.
Right. So another question, Eric, everywhere in the state they find something that's suitable with gas. Really, it comes down to even something that I think we can invest around a little bit. I'd like to learn more from the panelists or members of the audience. It's really how the transportation factor involved in the economic equation. Because I've always been told as a geologist that, okay, you want to sequester carbon in an area and then put it right in the ground without transporting. You can transport, quote unquote, and economic factors out the window, just to rely on subjects. So that's a bit of a divergence in my answer, but I'd like to talk about that at some point. So we are limited, really, quite now, to areas near pointers. Those pointers are going to be along the I-15 corridor, along the I-70 corridor. But if we are able to move into northern direct air capture technology, which is something that's been long promised, that's really been economically and really scientifically feasible to implement. We can apply it all over the state. These point sources or direct air capture can be placed in very rural areas to represent a tiny point. Part of your economic revitalization is to maybe place these some sequestration sites in counties that may see losses from maybe, limiting, coal jobs or limiting oil and gas reserves in certain areas. So we can place treasury capture hubs in the area, really anywhere in the state. Geology is not limiting factor, like only concept can make it work. That I think is going to be more so the factor that we have to consider more certain than geology. Thinking about it.
Any more? No, that was great. I mean, that was outstanding. I was blown away, speechless. Reed, you have a follow-up?
Yeah, I think, well, just following on his comment, to be able to plot direct air capture sort of anywhere would be really amazing. You would still, as was mentioned, I think earlier today about the energy consumption of direct air capture, not to mention just the horrible economics at the moment, right? And this hope of a learning curve and, dramatically decreasing costs. I think I have to mention, I really think, so hydrogen has the three pillars that it for its massive subsidy, right? One of those is additionality. I think that there could be an issue with CCUS and direct air capture specifically if you were to bolt them onto the grid and just pull power from the grid, trade a few certificates, and then leave everyone else where their next marginal megawatts are coming from fossil. So all you've done is spun everyone's wheels and wasted a whole bunch of time. Pulling some CO2 out of the air and then forcing a whole bunch of other people to burn more fossil fuels. And so it's like but this is why I think that pairing with maybe a locationally agnostic geothermal power source would be very cool, particularly if you can apply, say, 80% of that, say 80% of your DAC process energy consumption was actually just direct thermal application to, say, your sorbent material for regeneration. Like the sky's the limit. I think if we can put those three things together, direct air capture, geothermal, and obviously the subsurface is acceptable, suitable to it. But it sounds like we can go anywhere. Nuclear, DAC. Yeah. Whoa, there's like 26 people in that Milford that complained about the seismicity. Oh.
Okay, so to address some of the questions that were presented earlier, so would one of you be willing to speak on primacy?
The state's ability to regulate and issue permits for Class 6 injection wells. Yeah.
Oh, yeah.
John can talk about.
Our sixth panelist, John Baza.
Better than 7 years, I was told.
And then from the moment of state primacy, what's the inside or outside expectation for permitting time for Class 6?
Why do I always think thermal market? Create the right model to analyze that one.
Ultimately, the EPA still decides. Primacy just means that the state gets to shepherd the process and speed that part of it up. It's still the black hole. Is that the word used? It's still yeah. There's still a.
for example, reservoir engineer, the state is gonna allocate to review those reservoir models. But and versus the amount of application that you are receiving. Because it's a very expensive process to review those applications. And it's a shared responsibility from the operator and the state, because the operator also has to make sure that the information is provided in a way that can be, I would say, accessible and repeatable.
I think something worth considering too is just commercializing is how can you move forward with any of these CCUS projects in the absence of like before we even obtain financing. How can we figure out how to layer in different phases where we still put the emitters together, you can still put the transmission together for class 2 injection for WAG for water alternating gas, figure out how to apply it to some of our oil fields where we can do enhanced oil recovery, and we can get this whole process started before even getting through class 6 or connecting to Rangeley. It's maybe it's kind of out there, but if we can get an emission source in eastern Uinta County over to Rangeley's CO2 field or connecting to Raven Ridge, like there I think are some weird paths that we can take to get all this stuff started before we even have primacy. And then the moment primacy happens, we're already in business, but it could improve our economics just a little bit, or at least improve our optionality on whether or not we're selling CO2 for EOR or simply, harvesting the $85 pure sequestration credits.
You had your moment earlier. No, all right, fine. Jump to the front of the line. Sid still got a question. Sid, you're up next. So.
It does get back to Sid's original question. One of his original questions about the net CO2 storage associated with EOR. That was your question, right?
Yeah, you're up. All right, fine.
I see so much now, not just in Utah, not just today, but other places where the energy transition, new energy concepts are marching forward, irrespective of facts, irrespective of sensibility, certainly irrespective of science. And here's the thing too, you didn't even address the two questions that Phil and I raised. When you look at the huge amount of carbon dioxide fossil fuel, does the meager amount of CO2 you could collect warrant the energy and the effort that's going into it? I doubt it. Second thing is, shouldn't one have started out right from the front to say under what conditions does it actually reduce CO2? And so we are all, and I have to admit, I fall in that trap too, the blame of acquiescing with this marching along, whether or not facts are ignored or not. Now, I really agree with what the friend said about economics. I think energy and energy related is so big that there's huge new economic benefit things that can come out of it. But they need to be profitable. Now, certainly carbon dioxide capture wouldn't even exist if it wasn't for the $85 a ton and $185 a ton. I mean, it's all government driven. And yet our government is spending so wildly that can't go on. Now, I'm all for economic benefit, and I'm pleased that our state also puts priority on that. So we really do. And I'm for that. And there's plenty of business opportunities. We heard two small companies talk today about new technologies for geothermal. They're highly unlikely they're going to work out, at least not as they said. Surprising, but they're doing great things. They're both moving forward, and it's very likely they'll have to change several directions to keep going, but that's very good. And they're doing it for economic reasons. And they're trying to make it make sense from economic reasons. So you all are all day on the panel. You didn't pick up on these stupid things. Not you, I.
Question there?
Thank you, Sid. So real quick, so just to address the EOR from the EOR economic standpoint or storage standpoint, within the state, are there options for EOR within the state?
Where the EOR field candidates,
Yeah.
guys that aren't currently, I mean, because it's Elk Resources, Indiana, and
Was Resolute, then Elk, and then, no one, Dr. Dev led a study of the Uinta Basin and its readiness for CO2 EOR.
Get some of that CO2 in
DMBO.
basin to actually inject it out.
Well, there's two sources. One is Bonanza Power
Yeah,
Plant.
sure.
Okay. The other is, of course, Reed already mentioned it, is the tie-in from Rangeley. That CO2 is already consumed, but the infrastructure is poised to make that happen. So I want to bring it back and tie John's question to Sid's question. That is the EOR and you mentioned, Sid, that it's just there's no point in storing CO2 because there's no net storage of CO2. Is that your statement?
Cycle analysis to successfully show whether or not carbon capture and sequestration actually lowers carbon dioxide emissions or whether it increases.
There's a group out of
Not complete cycle. That's what I said. I don't even know who you're gonna make it, but I don't. Cycle.
the Edmonton group focused just on EOR. And it was an LCA of
Carbon dioxide holds it up back to the Gulf of Texas. And calling that sequestration is just not true and say, well, we'll put that.
No, that was
Well,
exactly, that's what their caveat said, was that they said basically the same thing. They said that if you do not factor in the combustion, which is going to happen anyway, that's their contention, then it is net positive. But if you factor in the combustion, it's not. But the combustion is going to happen no matter what, right? So do you just throw up your hands and give up at that point?
so you hold your nose and inject. You just
I don't think so. See, I think the United States has limited resources of people, labor supply, technology, and certainly limited money, even though we're a rich country. And so therefore, we ought to put that into the highest priority to combat this climate warming. We're not doing that. We're marching down the road without looking at the whole picture. And I think we ought to be using our resources better.
Thank you for your comments, Sid. We'd like to thank everybody, the panel for attending, and on that, we are done.
Thank you, Eric. Okay, just to remind everybody, dinner's at 6 p.m. right across.